Hello everyone, my name is XIANG and we are from Group 3. Today we want to do some discussion about good assignment, which is modeling coilover suspension with second order ordinary differential equation. What is coilover? A coilover, short for coil spring over shock absorber, is a type of suspension device used in car, motorcycle, and motorsport vehicle. It combines a coil spring and a damper into a single compact unit. The function of spring is support the vehicle weight and determine the ride stiffness. The function of damper is control how far the spring compression and rebounds and prevent bouncing and improve ride stability. The next part is derivation of the second order ODE. The spring restoring force is equal to negative kx, and the damping force is equal to negative cv, and v can be written in terms of the xt. And by Newton's second law, the resultant force of an object is equal to its mass times its acceleration, and we can write F spring plus F damping equals to ma. After arrange all of the equation into left side, we will get the characteristic equation mr squared plus cr plus k equals to 0, and the rules can be found by using the equation r equals to negative c plus minus square root c squared negative 4mk over 2m. Next part is then oscillation function for different scenario, and our group set mass equals to 3.541 kg and spring constant is 6.423 Newton per meter, and C critical can be found by using the equation 2 square root m sine k, and we got the C critical is 9.538 Newton second per meter. And first scenario is undead oscillation, and C will be equals to 0, and we assume the spring is gauged by 1 meter due to bumping rho, and the initial velocity is 0, and using the equation 1 to find the rho, we got the R1 and R2 equals to 0 plus minus 1.347 mi. I stand for imaginary number. Next, we use xt equals to e alpha t bracket a cos beta t plus b sine beta t cos bracket, and differentiate this equation, we got negative a beta sine beta t plus b beta cos beta t, and we're using these two equations to find the value of a and b, and when t is equals to 0, x will be 1, so we got the a will be 1, and when t equals to 0, v will be 0, so we got the value of b equals to 0, and the final equation of then oscillation will be xt equals to cos 1.347 t. Using the equation xt equals to cos 1.347 t, we plot the gross displacement versus time by using demos.
Now, let's look at the underdamped case of a mass spring damper system. Underdamping means the system still oscillates, but the amplitude slowly decreases over time. It happens when c squared minus 4mk less than 0. So using our values of mk and c, we get negative 86.47, which is less than 0. So this is clarified that the system is underdamped. We also need to calculate the alpha value and angular frequency value. We assume the initial condition x equals to 1 and x prime equals to 0. So from this, we find that a equals to 1 and b equals to alpha over angular frequency, which is we got 0.2285. And then here's the final solution. So this is the graph of underdamped oscillation, displacement versus time. From the graph, you will see the wave starting at its maximum and then gradually shrinking in height over time. The peaks get lower and lower until the motion dies out. This is typical of underdamped systems, such as a car suspension going over above, a door with a soft close hinge, or even a guitar string that slowly fades after being plucked. To sum up this underdamped oscillation graph, our damping is light enough to allow vibration, but strong enough to reduce the motion over time, and the system is underdamped and the motion decays exponentially. This type of response is very common in real-world mechanical and electrical systems, especially when we want things to return to rest smoothly, not too slow and not too fast.
So next, we are going to the overdamped condition, and for this condition, our damping ratio is greater than 1. So our C, which is damping coefficient, is greater than our damping coefficient for critical conditions. So the equation for the condition is given as shown in the slide. And then we will normalize the forms by divide the equation by m, and we will get a new equation as shown in the slide, where omega naught is equals to sec k over m, which is our natural frequency, and our damping ratio is equals to c over 2 sec mk. So next, we are going to solve the ODE equation by letting dx over dt equals to r. And then by using quadratic formula, we will have the equation to find our r. So for this condition, the roots are real and has two roots. So the equation is xt equals to a exponent to the power of r1t plus b exponent to the power of r2t. To generate the graph, we will need the constant value. So the constant value for m and k has been determined as shown in the slide. So after that, we will need to calculate the omega naught and our damping ratio, also our damping coefficient, and the value has been shown in the slide. Then we will use the quadratic formula to find our r1 and r2. We will sub in all the constant value into the equation, and then we will calculate to get the r1 and r2. So to find our a and b value, we will use two equations, which is x when t is equals to 0 and x prime when t is equals to 0. After that, by using the substitution method, we will get the a and b value. Then we will enter the a and b value into our main equation. Then we will get xt equals to 1.201 exponent to the power of negative 0.551t minus 0.201 exponent to the power of negative 3.293t. This is the table and the graph for the overdamped condition. We change the time in second to get the result of displacement, our xt. So the relationship between these two variables has been shown in the graph.
For the critically damped condition, the damping ratio is actually equals to 1. That's why C is equals to C critical. And after getting the equation for R, it can be split into the left side and the right side. And the right side is equals to 0, hence the value of R is equals to negative C over 2M. And after getting the value of R, it is found that there's only one root for critically damped condition. That's why the general solution used is xt equals to A exponent plus BT exponent. And using the condition of t is equals to 0 when x is equal to 1, we can get the value of a, which is 1. And after differentiating the equation and using the condition t is equals to 0 when the x prime is equals to 0, and we will get the value of b, which is 1.347. And hence we will get the solution for this, which is e exponent negative 1.347 t plus 1.347 t e power of negative 1.347 t. And this displacement against time graph represents the critically damped condition, which we can see that the system can quickly return to its equilibrium position in the shortest time possible with minimum oscillations. For discussion, the undamped system exhibits pure sinusoidal oscillation with constant amplitude, which is not realistic, while the undamped system shows decaying oscillation, making it a suitable model for comfort and stability. And then the critically damped system returns to equilibrium the fastest without any oscillation, representing the ideal case. And lastly, the overdamped system, while non-oscillatory, returns slowly to equilibrium, indicating excessive damping and sluggish response.